We have created mountains and valleys. What now? As soon as mountains start to growing, erosion will occur and sediments will be produced, transported, and eventually deposited in subsiding domains. All these components of the system are strongly influenced by precipitation, temperatures, in summary, by what we call climate. Climate is the weather measured over tens of years. It includes knowledge of temperature, humidity, atmospheric pressures, wind, and precipitation. The motor driving climate, as well as many other processes, is the energy generated by the sun. This is a huge amount and is roughly constant through time. Part of this energy is absorbed by the planet, part reflected back into the atmosphere. The balance between these components is key for the Earth climate and has made it possible to keep temperatures on the Earth generally constant and pleasant. To understand climate and climate changes, we need to look more in detail at how energy is transmitted. The energy from the sun to the Earth is transmitted by radiation. This implies no contact between the emitting and the receiving bodies and no significant movement or mass between them. During its travel from the sun, radiated energy will interact with the atmosphere and eventually with the Earth. Energy radiation and interaction with various bodies follow a number of very important rules. All objects absorb and emit radiant energy. Good absorbers are also good emitters. Poor absorbers are also poor emitters. Hotter objects radiate more energy per unit area than cold objects. The hotter the radiating body, the shorter the emitted wavelength will be. The wavelength of the sun radiation, for instance, is much shorter than that of the Earth. Following the rules mentioned in the previous slide, we can now look at what happens to the energy radiated by the sun. Being a very hot body, the sun will emit a very high amount of energy, typically with short wavelengths. Having short wavelengths, the sun energy will easily pass through the gases present in the external part of the atmosphere and will then reach the clouds, which will reflect back to the atmosphere part of the incoming energy. The largest part of the energy, however, will then travel further and reach the surface of the Earth. Energy hitting colder reflective bodies like glaciers and water masses will be essentially reflected back. On the whole, this energy is not very much. A substantial amount of the energy, roughly half of the incoming amount, will interact with the continents. Soil, vegetation, and so on will absorb large amount of the energy and then emit it back. But something very important happens at this stage. Namely, the energy emitted by the Earth has been changed and has acquired much longer wavelengths than the one which was delivered by the sun. This is in accordance with our rule number 4. The energy emitted by the Earth will then start traveling backward towards the high atmosphere, but will then be blocked by clouds and, more importantly, by the layer of greenhouse gases. Because of the higher wavelengths, the energy emitted by the sun can Earth. Energy is then trapped between the Earth's surface and the layer of the greenhouse gases, thereby creating an overall pleasant temperatures we are enjoying on Earth since millions of years. It is clearly a very complex system with a lot of variables which, however, are closely interlinked, and even small changes can have profound consequences. These fall under the general category of climate change. Here are some examples. The greenhouse gases form essentially a blanket bouncing back the infrared rays emitted by the Earth. An increase in greenhouse gases, like the one we are experiencing now, leads to an average increase in temperatures. Albedo is the percentage of reflected energy with respect to the incident energy. Clearly, glaciers have a very high albedo. Decrease in the surface of the glaciers decreases the portion of the sun energy radiated back to the atmosphere, resulting in an increase in the energy absorbed by the Earth and emitted back as infrared. A third very important component is vegetation. And here things start getting complicated, as vegetation has a twofold effect. Increase in vegetation also increases the emission of CO2, an important greenhouse effect. On the other side, when plants die, CO2 is buried as fossil. As you see from the diagram, there have been important changes in temperature in the past. Indeed, climate has always been changing, and this has happened over a multitude of temporal scales. Changing climate has had a major impact on the type of sediments, living conditions, and many other features. At present, we are facing an additional challenge, namely climate change caused by human activities. Specific climatic conditions in a specific place in the Earth, for instance, the one where you are living, are very much controlled by temperatures, winds, precipitations, and ocean circulation. The first order distribution of these phenomena can be understood by looking at how the energy radiated from the Sun is distributed over the Earth. These are the issues we will discuss in this clip. In a very short journey, I will present you the distribution of temperature on the Earth and the main patterns of wind circulation, precipitations, and ocean currents. This knowledge is critical for geologists to understand the production, distribution, and deposition of sediments. The most important factor controlling temperature in a specific plate is the amount of energy per square meter. This depends, among other factors, on the distance from the Sun and the angle the surface makes with incoming rays. Areas such as the one indicated with a red ellipse are close to the Sun and are roughly perpendicular to the incoming energy. These places will be very hot. I wonder how many of you are living in these regions. Areas like the ones indicated with a blue ellipse are further away from the Sun and are very oblique to the incoming rays, resulting in a much smaller energy per square meter. As a result, temperatures are distributed along east-west trending bands with similar values. These bands oscillate in north-south direction during the years and during larger time periods. Winds are another first-order component of the climate system. Among many other functions, they carry energy, water vapor, and exert a first-order control on precipitations. The global pattern of wind circulation is controlled by the temperature distribution we have just seen. The rules are simple. The air overlying high-temperature regions will become warmer, decrease its density, expand, and move upward, forming areas of low pressure. In cold regions, on the contrary, air will become heavier, descend, forming regions of high pressure. In a fixed and simple Earth, air will circulate along two large cells. It will rise in correspondence of the equator, moving then towards the poles, where as it becomes cooler, heavier, and will descend, forming a first-order cell. In reality, the first-order cell is broken in smaller cells, 3 on each hemisphere. Air rises in the equatorial region and descends in the tropical regions. Note also that because of the Earth's rotation, winds will be deviated according to Coriolis force. In the northern hemisphere, they will turn west when descending and east when ascending. The map shows the first-order patterns of wind circulation. The equatorial regions are characterized by areas of low pressure, with air moving upward and being attracted by higher latitudes and moving in a westerly direction. These are the famous westerlies. This region is called the intertropical convergence zone. To the north and south of the intertropical convergence zone, two areas of high pressures are found where air masses move downwards and are pushed towards the east. In the map, you can also see a new and very important effect, namely that generated by continents and high mountains. If you look at Central Asia and surrounding regions, you know the presence of a large high-pressure zone, which is caused by the very low temperatures associated with the Himalayan mountain belt. The monsoon winds are a first-order consequence of this pressure distribution. Winds are the driving force controlling another fundamental component of climate, namely precipitations. The key observation is that the amount of water which can be dissolved in air is strongly dependent on temperature of the air mass. Using the plot in the slide, let us make an example. The air mass indicated in the ellipse has a temperature of around 15 degrees and according to the plot will contain 1% of vapor. If the air cools down to minus 20 degrees, it can only contain less than 0.5% of water vapor. Water vapor is expelled and precipitations are generated. Based on these principles, we can predict that precipitation will develop there where air masses move upward and are therefore cooled. This happens in two first-order places: in areas of low pressures and in mountainous regions where winds coming from the sea are obliged by the mountains range to move upward, discharging water on the one side and resulting in dry conditions on the other. The Himalayas are great examples, with the huge precipitation on the southern side contrasting with the arid conditions in the north. In the slide, you see a typical map indicating distribution of precipitation over the Earth. Largest amount of rainfalls is indeed in the equatorial regions, where air masses are heated up and rise. Having looked at the distribution of sun energy and the resulting temperatures and wind patterns, you are now ready to look at ocean currents. Ocean currents are of the greatest importance in the Earth. They can travel for thousands of kilometers, distributing heat and affecting temperatures in large parts of the globe. The Gulf Current is one of the most famous examples. A profound knowledge of current patterns is of great importance. Think, for instance, at the search of the relics of the MH17 plane, which disappeared recently in Southeast Asia. Large-scale oceanic currents are essentially driven by winds. In the equatorial region, they will be pushed by the westerlies towards the west. In the tropical region, they will, on the contrary, move eastward. In strong contrast with wind, however, ocean currents are blocked by continental masses. In the Atlantic Ocean, for instance, water masses moving from the Gulf of Guinea towards the west are obliged to diverge to the north and to the south once they interact with the Brazilian continent. As a result, ocean circulation is characterized by gyres, which are domains characterized by an overall circular water circulation. In the previous clip, we have seen how the energy radiated from the sun interacts with the atmosphere and the Earth and controls the distribution of temperatures and the first-order pattern of wind circulation on the globe. Temperatures and winds interacting with continents and ocean control precipitations and ocean currents. Temperatures, winds, precipitation and currents, all major players in controlling climate and exerting a major influence on the distribution and type of sediments. Because climate is so dependent on a large number of phenomena often interacting in a very non-linear manner, climate change is the rule rather than the exception. Scientists predict that climate change will impact a large variety of phenomena, some of which are shown in the slide. 10,000–15,000 years ago, the climate was also very different from what it is now. Huge mammoths were walking around in what is now my office, and herds on giraffes and crocodiles were populating the vast sandy regions of the present Sahara Desert. Reconstructing climate changes occur in the past and understanding the controlling processes is of great importance. It helps in developing better scenarios for climate evolution in the future and to improve our ability to predict the type of sediments we might find in the subsurface of the Earth. All first-order tasks of you, future geologists. Already from the two examples shown in the previous slide, you can see that the climate has changed in different times of the Earth history, with very different wavelengths and consequently driven by very different processes. Let us look at some examples. We'll start with phenomena which have taken place in the recent past, geologically speaking, obviously. In the plot displayed in the slide, you can see two curves showing the changes in carbon dioxide and in temperatures over the last 400,000 years. The data are obtained from ice cores from Antarctica. The two curves show important oscillations, with temperatures values oscillating by nearly 15 degrees, huge changes. At times, temperatures were low, and presumably large ice sheets covered large parts of the Earth. In the interglacial period, temperatures were higher. During time periods with low temperature, glaciers were very widespread. large amounts of water were trapped in the polar regions and sea level was lower than at present, exposing large parts of the continental shelf. Because of the cold climate, only limited vegetation was present, a large amount of terrestrial sediments were transported to the sea. In the North Sea, for instance, sea level was so low that villages developed on the Dogger Bank, a region presently under 10 meters of water. In warmer interglacial periods, such as the one we are living now, the ice caps are small and the sea level high, resulting in continental shelves largely underwater. Vegetation can flourish, thereby limiting the amount of sediments being produced and delivered to the sea. Let us now look in more detail at changes shown by the curves. At the right hand of the diagram, you see a major increase in CO2. This increase has been associated with the beginning of the Industrial Revolution and is considered the driver of climate change. If you now look at the remaining part of the diagram up to 300,000 years ago, it is clear that major changes have taken place in CO2 and therefore temperature. A striking feature of the curve is the cyclic pattern. This means that temperature oscillates with a recurrent time length and not in a random manner. A very clear wavelength is indicated by red arrows and correspond to duration of about 100,000 years. Shorter wavelengths are also visible, such as the one marked by the blue arrows, which is roughly 20,000 years. What is the origin of these irregular patterns? The changes mentioned are related to regular modification of the position of the Earth with respect to the Sun, and therefore of the amount of energy received by a certain region through time. From astronomical studies, we know of three major cyclic changes. Together, they are called Milankovitch cycles. Precessions refer to slight changes in the angle of the Earth's rotation axis. Obliquity refers to the angle the Earth axis makes with its plane of rotation, which is called the ecliptic. Eccentricity refers to slight changes in the ellipticity of the orbit of the Earth. As a result of these subtle changes in the position of the Earth, the amount of energy irradiated reaching a specific surface of the Earth changes regularly through time. This can result, for instance, in regular modification of the temperatures, which itself has an impact on the amount of organisms living in a certain lake or sea. In the picture, you see a beautiful example of sedimentation modulated by Milankovitch signal. Here, the whitish layer are rich in carbonates, while the darker ones have a higher proportion of shales. Climate change can also occur at a larger time scale. The two curves on the plot show changes in temperatures and sea level during the last 600 million years. Clearly, the two curves change in a parallel fashion, raise an interesting question on why this occurs. In the plot, you can recognize also some fairly regular changes, this time at wavelengths of tens of millions of years. These are less defined than Milankovitch cycles and must have the very different underlying causes, possibly related to plate tectonics. A time interval of great interest is the Cretaceous, which was characterized by warm climate, high sea level, and thereby limited production of terrestrial sediments. In a previous clip, we have shown that the plate tectonic setting in Cretaceous time was characterized by a large ocean elongating in east-west direction, which resulted in weak currents. Hot temperatures, little terrestrial input, great conditions for hydrocarbons to develop. Not surprised that very large portion of the rocks generating petroleum were deposited in this time frame.